Okay, so in this second part, I'll talk about share-based fairness notions for the situation in which agents have arbitrary entitlements, not necessarily equal. So just as a reminder, we have a set M of n indivisible goods. We have n agents. Each agent has a monotone valuation function over the goods. A special case can be additive valuations that we've seen before. And each agent has an arbitrary non-negative entitlement, which we denote by DI. In the special case of equal entitlements, the entitlement of each agent is 1 over n, all have the same entitlement. So some assumptions, what does this BI represent? What's the semantics behind this BI? So first, higher value of BI is better, higher entitlement is better. This is in a qualitative sense. And in a quantitative sense, we should think of the BIs as being in some linear scale, in the sense of having twice as much entitlement is twice as good. Or another way of thinking of it is that if an agent J transfers her entitlement to agent I, then the new entitlement of agent I would be the sum of the two entitlements. So in some sense, we think of it as being in a linear scale. And we also assume that entitlements sum up to 1. So this indicates that collectively all agents are entitled to all of the goods, not less and not more. There is also literature at what happens when the entitlement does not sum up to 1. There's a lot of Talmudic literature that you may have heard of, such as Shnayim Ochazim Betalit, or things like that, in which what you should do if entitlements do not sum up to 1. So examples, similar to examples that we've seen before, like allocation of housing units to eligible residents, like in Mechir Lamishtaken that I mentioned. So there, for example, it is typical that if there's a project in a certain city, those eligible candidates who live in that particular city have priority over those who don't live in this city, so it's unequal entitlement. Allocation of seats to the parliament to political parties, so the number of votes that a political party received in the elections determines its entitlement in terms of number of parliament seats that it gets. Dividing an inheritance among a widow and several children, so it could be that the widow is entitled to half the inheritance and each of the two children to 1/4 of the inheritance. Handling student registration to courses of limited capacity, so maybe third-year students have priority over second-year students, or the NBA draft that I mentioned before. So basketball teams who finished lower positions in the previous season have higher priority over those who finished in the higher positions. So again, an example of unequal entitlement. So let's recall what we had for equal entitlement. So we had this ideal fairness notion that represents what we aspire to achieve. They are not always feasible, so sometimes instead we settle for some approximations of them. So for share-based notions, we have the max-min share. For the special case of additive valuations, we also have the proportional share, which is appropriate maybe for additive valuations. Again, we cannot always achieve them. We might think of what kind of approximations we can get. And for comparison-based notion, we had where you compare what you get to what others get. We had NB freeness. And of course, again, we had some approximation of it, like EFX or EF1. So this was what we had for equal entitlement. And we can ask what would be good definitions when the entitlements are not equal. These definitions are, except for the proportional share, which you can think of. It's easy to see how to generalize it for general entitlements. The other definitions do not seem to be easy to generalize. So what will we do here? We'll try to present fairness notions that apply to arbitrary unequal entitlements and that apply to all monotone valuations, not specifically to, let's say, additive valuations, but all monotone valuations. We will will not discuss comparison-based notions like envy-freeness. There are attempts to extend envy-freeness to unequal entitlement and have been used in papers. Personally, I don't like them, so I'll not discuss them. I can later discuss why I don't like them. But so I don't think there are. My feeling is that it's still an open question of what kind of envy-based notions are appropriate for unequal entitlement. So we'll concentrate on share-based fairness, and we'll present three notions, like MMS hat, it's a variation on the max-min share, MES hat, a variation on the max expectation share, and a new share, the any price share, that has some nice properties. So we'll start with these things. So we'll first present some definitions and then mention some results. Okay, so now we want the ex-post share-based fairness notions. So recall the agent has an entitlement BI, which is non-negative. The sum of entitlements is 1. For equal entitlement, this means that every agent has entitlement 1 over n, but more generally it could be different. And the question is, what would be a good share notion? The problem, like, how would we generalize something like the MMS share? The problem with the MMS share was it said you partition the items into n parts of, let's say if there are n agents, and you get the worst part, but if they have unequal entitlement, why should they all be entitled to the same thing, like a part? So in the special case where your entitlement is 1 over an integer, 1 over k for some integer k, you can think of using the MMS, but not partition into n parts, but partition over k parts, because you say if my entitlement is 1 over k, if I was in this situation with equal entitlement agents, there would be k agents, then I would be partitioning it into k parts and get the worst part. So I can take the MMS, but with respect to like entitlement 1 over k, not 1 over n. So this is a natural thing that we can do if the entitlement happens to be of this special form. So suppose that this is what we actually choose to do, and then the question remains, what would be the share value when your entitlement is not of this special form, but it's something between, let's say, smaller than 1 over k and larger than 1 over k plus 1. What should you do? So the first approach that we'll discuss is just you round your entitlement up or down to the nearest, like 1 over k or 1 over k plus 1. So this is one option. So one version is what I call pessimistic rounding. So you round your entitlement down in this case. And then your MMS down would be like your MMS as if your entitlement was smaller, just 1 over k plus 1. You partition the items into k plus 1 bundles and get the worst one. What would be a motivation behind such a definition? So we can at least hope maybe that one thing that's nice about the MMS, max-min share, is that if all agents have exactly the same valuation function, the MMS is a feasible share. Each agent can get the MMS value. You do this MMS partition into n parts. Each agent is willing to take any one of the parts. So you can hope that the same thing would happen here, that if you do this rounding down, then you get a share that is feasible, at least in the special case in which all agents have the same valuation function. Okay? So certainly if there were, okay. So let's say if you had indeed k plus 1 agents, each with entitlement exactly 1 over k plus 1 to begin with, the rounding down would have no effect. You just keep your original entitlement, and indeed this share would be feasible if all agents have the same valuation function. So this is some possible motivation for this rounding down. However, it does not quite work. So there are instances with unequal entitlement, but of the form 1 over k, 1 is what would be half, 1/3, and 1/6, that in which the agents have identical added not just identical valuation functions, even identical additive valuation functions, in which this MMS down shell, you cannot give it to all agents. One agent will not be able to get it. So the fact that the MMS is feasible with equal entitlement does not extend to say that this MMS down is feasible with equal, identical valuations. So that's not true. So at least this kind of motivation for pessimistic rounding is not such a good motivation. So I just thought try to do this pessimistic rounding and let's be optimistic instead. Anyway, we're not going to get something feasible, so if it's not going to be feasible, let's be optimistic and try to give agents at least a higher share value. Anyway, it's not feasible and we'll need to approximate it. So approximating something higher is better than approximating something lower. So what we'll do is round up. So this is het MMS. We round it up. Your share value is the MMS as if your entitlement was 1/k, as if you were competing altogether your k agents. And what's an upper bound for this optimistic, like a motivation for this optimistic rounding, is that it's conceivable that it is an upper bound on all feasible shares, meaning that any share that you can think of, if it is a feasible share, meaning that you can always give the agents their share value, it cannot be larger than this. So this is some maybe universal upper bound. And indeed it is, for a very simple reason, because there might be k agents, all with this entitlement bi, so all would be rounded up to 1/k. And if they all have the same valuation vi like you, then at least one of the agents would get at most this share value, this MMS value. So if you want a share that is feasible, it cannot have value higher than this particular share. So this is a good upper bound. And in fact, this upper bound is tight. You cannot think of any lower share that would be an upper bound on all feasible shares, and even not on all nice feasible shares, which are not defined here. So there is a collection of shares that we can define, all kinds of shares, such that each one of these shares is feasible, meaning if we adopt these share notions, it's always possible to give all the agents their share value. It has some nice properties which I will not go into here, but it's not, this just means that it's not too crazy shares. These shares do make some sense. And whatever your valuation is and your entitlement is, at least for additive valuation, the value of at least one of these shares is exactly equal to this MMS head. So if you want to dominate all possible feasible shares, you have to take the MMS head. You cannot take anything smaller.
When you say that the share is feasible, do you mean that you can, even if they have different valuations?
Even if they have different valuations, different entitlements, you can always give it. That's what I mean by a share which is feasible. That in every allocation instance, every agent can get their share value, no matter what their valuation function is, no matter what their entitlement is. Okay, so in this respect, this is an interesting share to look at because it's a tight upper bound on all feasible shares. So now we'll go to a different share notion. So now we don't want an upper bound on all feasible shares. What we are now aiming to get is one particular share, not necessarily feasible, but that we think that in some sense is natural, is nice. Okay? So this share is called the enterprise share. Okay, we produce it Tomer, Moshe, and I in some previous work. So let's recall what is the MMS of an agent, the maximin share is the value she can guarantee to herself if she's a cutter in a cut and choose game. She cuts the set of items into n parts and gets the worst part. That's that's what she can guarantee to herself. She cuts it in the best way, and that's the work part. At the high level, the way to think of the any price share is the value that the agent is guaranteed to get, not as a cutter, but as a chooser, and not in a cut and choose game, but in a different game, which is price and choose, which I'll describe. The advantage of price and choose compared to cut and choose is that price and choose can handle arbitrary entitlement. Cut and choose, like you think of agents of being of equal entitlement because each one is entitled to choose any one of the parts, and price and choose can discriminate between agents that have different entitlements. So even if the entitlement is something of the form 1 of the K, since one definition talks about the cutter in cut and choose, and the other about the chooser in price and choose, they have like different definitions. So the value of the APS would not be equal to the value of the MMS. It's a new share. It's not an extension of the MMS to unequal entitlements. It's a new share. It's a different share. Okay, so here's the definitions. So what is the game? Instead of the cut and choose, we have a price step, and this an adversary does. The adversary assigns a non-negative price vectors to the items. That is, each item gets a price, a non-negative price, and the sum of the prices has to be 1. Okay, so the adversary can choose how to price the items. And then the agent may pick any bundle as long as the price of that bundle is not larger than the entitlement of the agent. So the entitlement of the agent is some number between 0 and 1, saying what the relative fraction of the whole goods is entitled to. So here, to measure whether he got this fraction or not, we measure it according to the prices of the goods as given by the adversary. Okay. So it's a min-max definition. You take the minimum over all possible price vectors of the maximum bundle among those that is allowed to choose given the price vectors. This is the any price share. So under any price, you can get at least this value, no matter how the items are priced. So this is the min-max definition. And as like just for shares, we also always require that the value of the share depends only on the valuation function of the agent himself, and it depends only on the entitlement of the agent itself. We don't care how the rest of the entitlement is partitioned among other agents. Okay. All you need to know is your own entitlement and your own valuation function in order to know what your share value is. So let us give an example. Suppose we are looking at a special case of additive valuations, and suppose your entitlement is not 1 over an integer. Let's say it's 2/5. It's not 1/2, not 1/3. And suppose we have these 5 items, 2 of them of value 7 and 3 of them of value 5. What would the share value be? So an adversary can price the items, these 2 as 0.23 and these 3 as 0.18. If you sum up all the prices, you actually get 1 as desired. And we can see what can an agent afford to buy. Can afford to buy 2 small items because the price would be less than 0.4. He cannot afford to buy 1 small item and 1 large item because together they are more than 0.4. But he can afford to buy 1 larger item. So it's better to buy 2 small items than 1 large item. This gives him a value of 10. So under this price vector, he can get a value of at most 10. He can get a value of 10. So the any price share is at most 10. It doesn't mean that it's exactly 10, because maybe there's a different price vector that I can give in which he cannot even get a value of 10. So to show that it's exactly 10, how do we show that? So we can arrange the 5 items in 5 bundles, each of them containing 2 items. So these are the 5 bundles, like AB, BC, CD, DE, EA. Okay? And each item appears exactly in 2 of the bundles. So no matter how you are going to price the items, at least one of these bundles would have price, if you look at the items in the bundle, at least one of them would have price at most 0.4, because the average price of an item is 0.2, so it will have to happen. So no matter how you price, I will be able to buy a bundle that contains 2 items, and since every bundle that contains 2 items has value at least 10, my value is going to be at least 10. So we have both a lower bound on the APS and an upper bound on the APS, so we know that the APS is exactly 10. So this leads us to another definition of the APS, this example that I showed here. For this definition, we introduced a notion, a well-known notion, of the distribution over subsets of items. So you have sets, and with each set of items, we associate a probability. Okay? And we call this distribution BI balance if every item has probability BI of appearing in a random bundle. So it has select a random bundle from this distribution, and according to this distribution, then the probability that the item is in this selection is exactly BI. So for example, this was a balanced distribution. If I give each one of these bundles probability 1/5, then if I look at each item, let's say item E, if I select a random bundle with probability 2/5, I'm going to choose either this or that. So it appears exactly with probability BI. Okay, so this is a balanced distribution. And a max-min definition of the APS, and it's equivalent to the APS, this definition, is the value of the worst bundle in the best BI balance distribution. So this is another definition of the any price share. Okay. And the proof that they are equivalent is by linear programming duality. For linear programming duality, you can show that these two definitions give the same value. So the APS has like 2 definitions, a max-min definition and a min-max definition. One of them you can use as a way of giving an upper bound on the APS, the other is a lower bound, and they must match. For equal entitlements, let us remember what the maximum share is. So really, the definition of the MMS, the maximum share, is the same as the definition of the APS, except that we require in the balanced distribution that the bundles are disjoint. So let's say if you have entitlement 1/3, you have to partition the items into 3 bundles. So if you give each bundle probability 1/3, then each item is selected if you select a random bundle with probability 1/3. So the definition of MMS requires a partition into disjoint bundles. The definition of APS allows partition also into overlapping bundles, as we did before, and this gives it some extra power. So for this reason, even if you are in the case of equal entitlement, the APS is at least as large as the MMS, and is sometimes even strictly larger. Okay. So we define the APS, and we can try a sanity check to ask, is it a good fairness notion in the sense, does it capture our intuition of what fair allocations should do? And there is a special case in which we have a good intuition of what we want the fair allocations to do, and this is dividing a homogeneous divisible good, something that you can keep on dividing, and when you get a part, you care only about the size of the part that you get, you don't care like whether it came from the left or from the right. So example of homogeneous divisible goods are money that you can keep on dividing, water, processing time, storage state, things like that. The way we model it, if we want to model it as an indivisible item, you can think of m identical items for some very large m, and the items are identical. And when we say that they are homogeneous, we mean that the value of a set of items, the value of a set of items is just what you care is only the number of items that you get, and it's the value of getting this number of items. So the value of a gallon of water, it doesn't matter if I got the water from the left-hand side of the pool or the right-hand side of the pool, it's just a gallon of water, how much water I get. Okay, and in these cases, when you have a divisible good, there's an obvious allocation to choose. So each agent, if he has entitlement BI, he should get BI times n items. Assuming that, okay, m is large enough so that BI times n is an integer, you choose it in such a way. So this is like the natural thing you do when you divide a homogeneous good, when you have arbitrary entitlement. So let's say there's an inheritance of $1 million, and the widow is entitled to half, and each child is entitled to 1/4. Like, it's a no-brainer thing to say that the widow should get $500,000 and each child $250,000. And you don't ask them even what are your valuation functions. So we are not assumed that valuations are, yes, sure.
I'm sorry, I didn't mean to interrupt you in
Yeah.
the middle of the sentence. I wanted to suggest maybe that this consideration could be extended to non-homogeneous and indivisible goods by giving people shares in the entire bundle of goods. So if there were just two of us and you were entitled to 3/4 and I was entitled to 1/4, we could start by saying you have a 3/4 entitlement, I have 1/4 entitlement, and then we trade to a competitive equilibrium. Now, because the goods are indivisible, we might have to use probabilities there, but that would be.
Yeah, so there is this notion of competitive equilibrium that is used as one possible fairness notion. Let me say that in every competitive equilibrium, if it doesn't always exist, but if it exists, then each agent gets at least any price share. So in this respect, this is compatible with what I'm saying. But in general, it does not exist, competitive equilibrium for indivisible goods.
But I was suggesting
If you do things
if you allow for probabilities.
Yeah, so for probabilities, it means that ex ante.
Ex ante.
Yeah, so for ex ante, you can do things, for ex post, no.
Okay.
Yeah.
Essentially making the item divisible.
Yeah.
If you allow probabilities, it's
Yeah, that's
essentially
what
making the
I
item
that's what I was saying.
Yeah.
But
Okay.
maybe
Another-
ex ante is enough.
No, but, yeah. Okay.
Right.
Yeah. There are other issues, like the way, if you think of probabilities, like giving fractions of items, if valuations are not additive, you run into additional problems, maybe. Makes it more difficult to define what your valuation function is for over fractions of items. But, okay, we can discuss it later. Okay, so I'm saying this proportional allocation, you don't even ask the agents for their valuations, and I'm not assuming, for example, that your valuation function is linear, even if, let's say, what you're dividing is money. It could be that having $2 million is not twice as good than having $1 million. I'm not saying anything. So you don't ask them what their valuations is. What I'm claiming is the proportional allocation is probably what you're going to do when you have a homogeneous divisible good. And in the equal entitlement case, the ideal fairness notion that we saw, the MMS and the ME3, all are satisfied by this proportional allocation. So let's check what happens with the APS. So I'm saying that also with the APS, when you divide a homogeneous divisible good, you get exactly pi times n items. So how do you see that you cannot get more? So you can price each item as 1/n, and you can afford then exactly pi times n items. items, so you cannot get more. And a lower bound, you have to show a PI balance distribution with n bundles. So here's the distribution. Let's say your BI times n is 5, maybe you, n and BI have this relation. So I can arrange the items. So let's say these are all the items. I can partition them into n bundles, each with 5 consecutive items, give each bundle probability 1 over n, and then it's a BI balance distribution, and I must get at least one of these bundles in terms of value, so I get a value of BI times n. So the situation is when dividing a homogeneous divisible good, the proportional allocation is an APS allocation. Doesn't matter what the valuation function of the agents are. I never use this fact. For example, it doesn't have to be additive. And if valuations are strictly monotone, then the proportional allocation is the only APS allocation. Okay, that's even the only one. So you may say, okay, you can easily think of other shares that have this property. So I'm saying no. There were other suggestions for shares which did not have this property. There are suggestions for how to extend NB freeness to weighted NB freeness. It does not have this property. So it's not so easy to get this property. I'm saying the fact that APS achieves this property, you should think of it not as something trivial, but the way I think of it is that saying, yeah, this is probably a reasonable definition, and other definitions seem problematic. There are some other definitions that also attain this property, but there are definitions that do not. Okay, of course the APS is not a feasible share because the MMS is not, so even for equal entitlement it's not. It's not a feasible share even in a stronger sense because there are instances with indivisible items, even with equal entitlement and identical additive valuations, in which in every allocation some agent does not get their APS. It's another way of saying that even for additive valuations and equal entitlement, the APS can be larger than the MMS, strictly larger. So of course we'll settle for approximations of the APS, like we did with the MMS. Okay, and another share-based notion that I want to mention is for ex-ante allocation, what you get in expectation. So one option is to use the proportional share. Okay, so what is the value of the proportional share? It's PI times the value of the grandstand. And indeed you can achieve it ex-ante by saying each agent I gets the whole set of items with probability PI. And then you achieve this proportional share. And this is the best you can hope for additive valuation, but I want to point out that this is a very weak guarantee for other classes of valuation, let's say concave valuations or sub-additive valuations, in which the sum of values of parts is higher than the value of the whole. Because here you keep the good as a whole and give it to someone as a whole, and agents would really like you to partition the good. Yes, let's say you have m identical items, that each one agent, let's say n identical items and n agents, and each agent would be satisfied just with any one of the items, and additional ones don't give additional value, then of course they would like each agent to get one item, rather than one agent to get all the items, but only one item is worth something for the agent, and having the rest are all just substitutes to this one item. So the proportional guarantee is not such a good guarantee for general valuations. Yes.
So I I see the ex ante, and it means expected value. But what happens in fact? So is there any, maybe you already discussed, but what happens ex post?
No, so ex post, I showed the ex post we want to share like the any price share or things like that. In this particular allocation, ex post is terrible. I'm not recommending this allocation. I just say that this allocation shows that the proportional share is feasible ex ante. That's all I'm saying. I'm not saying it's a good thing. I'm just saying it's feasible.
So you can hope for something, but you
We'll
cannot
get,
really-
there is this notion of best of both world results, or you want things which are good both ex ante and ex post. We'll discuss it.
Or you could require Pareto optimality on top of.
This is Pareto optimal, giving everything, okay.
No,
if
it's
you-
not for suboptimal, not for,
No, for complete
Right.
substitute, if
Right.
there- but
Right.
if you are gradually increasing slowly and slowly, it is Pareto optimal. Like in
Yeah,
this kind
yeah,
of
yeah.
valuation.
No,
So,
that-
so Pareto would not get you out of it.
but the case of where you
Ah.
just want one good.
You want ex ante, okay,
Yeah.
ex ante Pareto can, so this ex ante is not Pareto. This is not ex ante Pareto. Anyway, we won't use this definition because, okay, because of this reason. It just offers too little when valuations are concave. Okay?
And
It's too weak.
The competitive equilibrium would get it down, it's also give everyone
Yes.
an equal share. You
Yeah.
would trade for something.
Yeah, if that, okay. Yeah,
Main issue is existence, because
No, but this is
competitive
ex
equilibrium
ante.
might not exist.
With probabilities.
but, okay,
With non-probabilities.
but non-additive, non-additive utilities, I have to think of it, whether it exists also in that case. If your valuation is not additive.
It should still exist because the probabilities convexify everything.
If your valuation is concave, you need the valuation to be concave?
No, I don't think you need
Okay,
anything.
maybe, okay. Okay, but so we'll introduce an ex ante share-based fairness notion, and we already saw something like this, the maximum expectation share, we saw it before, we defined it for equal entitlement, so let me give a different definition, not equivalent, that applies also for unequal entitlement. So we call the notion of a BI balanced distribution over bundles. Is one in which every item has probability of BI of appearing in a random bundle. And recall that the APS is the value of the worst bundle in the best BI balanced distribution. So the maximum expectation share is the expected value of a random bundle in the best BI balanced distribution. And because you look here at the random bundle and not the worst bundle, your value is at least as large as the APS. And because you're allowed to take a distribution in which you put one bundle with all the items with probability BI and the empty bundle with probability 1 minus BI, this is a valid distribution. You're also at least as good as the proportional share, but for concave valuation functions, you could be much, much better than the proportional share. So the ex ante share-based fairness notion that we consider is the MES. One of them is the MES. And now we want, like we had this MMS hat, a share that dominates every possible share ex post, every possible feasible share ex post. We want to do the same thing for ex ante shares. So recall the MMS is the expected value of a random bundle in the best BI balance distribution. And recall, like when we looked at the MMS hat, we rounded valuations up to 1 over an integer, 1 over k in this case. So we can have MES hat is the expected value of a random bundle in the best BI hat balance distribution. And this is going to be an upper bound on every feasible ex ante share, and it's in fact a tight upper bound. Okay. So a summary of share-based notions and specific, here, BI, think of it as being between some integer, 1 over k, k can be arbitrary, and larger than y over k plus 1, 1 over k plus 1. So these are tight upper bounds on all feasible shares. In the ex post case, we have the MMS hat is a tight upper bound, and in the ex ante case, MES hat is a tight upper bound. And if you are interested in specific shares with nice properties, So ex post, we have the any price shell. And what's nice about it is like in some special case of a divisible homogeneous good, it captures our intuition of what a fair allocation has to be. It's exactly captures the intuition. So in some sense, it's a natural shell. And the proportional shell is a shell that is always visible ex ante. These are special kinds of shells that we see. Okay. So now we shift just to additive valuations. So the shell notion that we saw here, except for the proportional shell ex ante, the other shells are not feasible. So we look at approximations, and the approximation ratio that you get depends on the class of valuations you look at. And we look only at what's considered the canonical class of valuation function that people look at, additive valuations. And we ask what kind of approximations we can get. So let's start with the MES hat. So if we look at additive valuation, then recall that in this case the maximum expectation share is exactly the proportional share, and then it is feasible. If we look at MES hat, then after rounding up, the sum of the entitlements already exceeds 1. And so the MES hat cannot be a feasible share because it like translates the entitlements to be larger than 1. So there's a simple proposition that says that after rounding, the sum of the entitlements is at most some number gamma, like it's an explicit number, roughly this value. Like what might happen under rounding? So it could be that one agent had entitlement half plus epsilon, and this was rounded up to 1. Another had entitlement 1/3 plus epsilon, and this was rounded up to 1/2. And another maybe had 1/7 plus epsilon, and this was rounded up to 1/6, and so on. So after rounding, that's the maximum that we can get. We can never get more than that. And that's the smallest possible upper boundary. Like for any number smaller than this particular gamma, I can find a sequence of entitlements that sums up to 1 that after rounding exceeds it. So what share is feasible for additive valuations? If I take the MES and divide it by this gamma, so this is roughly 0.591, and I give each agent I the grand bundle with this probability, you will get this share value, and so this is an approximation that we get for a share which is an upper bound on all feasible shares, so this simultaneously approximates all feasible shares. So now let's get to the ex post, which is much more difficult case. So here we want to approximate this MMS hat. So of course we cannot get an approximation ratio better than 1/gamma for the same reason as before, but we cannot even get an approximation ratio better than half, and here's a simple example. So suppose there are 2n-2 items of value 1. Suppose there are n-1 agents whose entitlement is slightly larger than 1/n, but smaller than 1/n-1. So when we round up their entitlement, it's rounded up to 1/n-1. So for each of them, he thinks that there are like n-1 agents, so the MMS, you have to partition it into n-1 bundles. Each bundle will have 2 items, so the MMS is 2 MMS hat for each one of them. And there's one agent of entitlement slightly smaller than 1/n, so that entitlement sum up to 1. So for this agent, BI hat is equal to Bn is equal to 1/n, and his MMS is 1. So he thinks he should get 1 item. Each one of them thinks they should get 2 items. So together they think they should get 2n-1 items, so too many items, not enough items to give all of them. One of them will miss an item. So the approximation ratio, one agent would get 1 item instead of 2. The approximation ratio is just half. You get only half of the MMS hat share. So you cannot hope for an approximation ratio better than half. So indeed, you can achieve this approximation. So we're only talking about additive valuation. So for every allocation instance with arbitrary entitlements and additive valuation, there is an allocation that gives every agent at least half of their MMS hat. And this particular allocation we know exists. We don't know a polynomial time algorithm for finding it, but we do know a polynomial time algorithm that for every epsilon you can find a half minus epsilon approximation to MMS hat. And in fact, the results hold not just with respect to MMS hat, but with respect to a stronger share called the truncated proportional share, and you can take the hat of this. So the truncated proportional share is something, we don't need to define it exactly here, it's something which is always at least as large as the MMS, never larger than the proportional share, and equal to the proportional share if no single item is over proportional, has by itself value more than the proportional share. So in many cases, this truncated proportional share is just equal to the proportional share. Okay. So this is the result that we have. So I want to say a few words about the proof technique for proving such a result, because it's through another allocation game, like we had picking sequences as allocation games. That's a new kind of picking sequence, like an adaptive picking sequence, in which players can influence who picks in the next round. And this is the bidding game. And what we'll do is design a safe strategy for this bidding game that guarantees the agent at least half the MMS hat, and then because each agent can follow this strategy, there is an allocation that gives each agent half of their MMS hat. And okay, we don't know if this strategy can be implemented in polynomial time. Okay, so what is the bidding game? It's taken from the same words that define the APS. Okay, so again, like in picking sequences, if we have M items, we have M rounds. So it's similar to picking sequences. So each agent gets some fake money, gets a budget equal to her entitlement BI. This is fake money. Has no value except in the game itself. When the game ends, if you still have money left, you just lose it. In every round, each agent makes a bid not higher than her remaining budget. The agent can choose which bid to make, but not more than she can afford with her remaining budget. The highest bidder wins the round, and we don't care how ties are broken. Then she pays her bid, so her budget is decreased by her bid, and she gets to pick one item of her choice, whichever item she wants. And then the round ends, and we go to the next round. And the game ends when either no items are left or no budget is left, and then the game ends. So we can assume that always, like no items are left at the end, and rather that no budget is left, because once only one agent has a budget, he can bid epsilon on each of the remaining items and take all the remaining items. So it cannot be that all agents run out of budget. So here's a natural bidding strategy in this game. So we call it the proportional bidding strategy. You can scale the additive valuation function so that the value of the grand bundle is equal to 1. So let's make the assumption that no single item has value above your entitlement after this scaling. And under this assumption, we'll show that this strategy achieves at least half of your proportional share. Without the assumption, we get half of this truncated proportional share, but I'll not show this. So what is the strategy? In every round, you just bid the value of the highest remaining item. So let's say the highest remaining item has value 0.1 for you, you give a bid of 0.1. Now, if you don't have sufficient budget, let's say your budget is only 0.01, then you'll bid your whole budget. So that's just the bidding strategy. And if you win the bid, you select the highest value item for you, and then we continue to the next round. So that's a very natural bidding strategy. So let's see how it works. So let's say you have two agents. You have entitlement 0.67, so that's your budget, and the adversary, think what's an adversary? It's someone who has the remaining budget and the same valuation function like you. So he wants you to get as little as possible because he'll get as highest possible value, so in a sense he's playing against you. Okay? And let's say we have two items, each of them worth half. So indeed, for you, no item is over proportional. No item has value larger than your total budget, like in the setting of the theorem. So what happens in the game? If you do the proportional bidding, for the first item, its value is half, so you bid half. The adversary can bid at most his full budget, which is less than half, so you win the item. In the second round, the budget that you have left after you paid your bid is just 0.17. So according to the strategy, you have to bid your whole budget, but the adversary can bid 0.33, and the adversary wins the second item. So that's what you have. So what value did you get? Exactly the amount of budget that you spent. Okay? So the fraction of the proportional share, because this was after scaling your valuation function, so the fraction of the proportional share that you get is at least the fraction of the budget that you spent. Why is it not equality? Because if you win a bid when you underbid, you get more value than what you spent. So to see how much you get, we just have to analyze how much budget you spent. Okay, so let's see that you got half your proportional share when there's no over proportional item. So if you manage to spend half your budget, you got at least a value of pi over 2, which is your proportional share as desired. So assume for the sake of contradiction, because this really cannot happen, that you did not manage to spend half your budget. So this means that you never needed to underbid. Why is that? So first of all, to begin with, no item was worth more than pi, so you could, for any single item, you can give a bid. Until you start winning items, you can give a bid. Once you start winning items, you might not be able to give bids because maybe you have insufficient budget left. But if your budget is more than p over, you spend less than pi over 2, it means that the last item that you won was more worth, it was pi over 2. So the next highest item still remaining also has value smaller than pi over 2. So you have enough budget to bid for it. So you really, if you spend only pi over 2, you never need to underbid. So the other agents, whenever they won an item, had to pay your bid at least, because they had to bid more than you to win the item. So they had to pay at least the value of the item for you. So regardless of which items they choose, the value that they consume is at most their total budget. Your budget is pi, their total budget is 1 minus pi. So you got a value of pi over 2, they got a value of 1 minus pi. So some value still remains in the game. They already spent all their budget. So you can keep on bidding and get more value. Okay? So this contradicts the assumption that you managed to spend only pi over 2. Okay, it doesn't contradict it. Unless you consumed all the items yourself, then. So, okay, so the value that you got is at least pi over 2.
Is there a version of this proof which uses second price auction and no
It's the same.
underbidding concept is there?
If you use second price auction instead of first price, it works exactly the same. There's no change in the proof. So, The bidding game has some variation. In some of them you can use second price auction instead of first price auction. Okay, so what did we see? We saw that the proportional strategy ensures at least half of the TPS, the truncated proportional share, which is also half of the MMS at least. But we need to achieve something better. Half of MMS head, something different, or at least, in fact, we achieve half of TPS head. So after rounding up my entitlement to something higher, I need to achieve higher value. And the proportional strategy is too weak to achieve this. So let me explain in what sense the proportional strategy is a weak strategy, it's not a good strategy. Let's return to this example that we've seen before. In the proportional strategy, I bid half on the first item. But I can instead, on the first item, bid lower than half. I can just bid slightly above the budget of the adversary. So I bid 0.335. Then I will win the first item, pay my bid, but still have enough budget left to also win the second item. So I can get both items, even though the proportional bidding strategy got only one item. So, of course, the proportional bidding strategy is not optimal. There are better strategies. Okay? So now, what are the requirements, if we can try to think of strategies and see counterexamples why they don't work and so on, if we want to achieve half of MMS head. So unlike the proportional strategy, which gives us half of the TPS, any strategy that achieves half of MMS head, we can prove, has to have the following properties. They are not sufficient, but they are necessary. It has to be non-myopic. It cannot be that you just look at what's the highest item still available and base your bid on this. You have to look at several items, see their values, and depending on the relation of these among these values, you have to choose what your bid is. You have to have some look ahead, see additional items, not just one item at a time. And perhaps even somewhat more surprising, it has to be non-monotone. So in the proportional bidding strategy, you bid the value of the highest item that still remains. The value of the highest item that still remains can only decrease as rounds go on. So your bidding is monotonically decreasing as rounds go on. We can prove that if this is what you enforce, you will not be able to get half of MMS head. You must have a bidding strategy that is non-monotone, meaning that as the high items disappear, you suddenly increase your bidding instead of decreasing your bidding. This is necessary. Okay, so to design a safe strategy for half MMS head requires a much better understanding of the strategy space of the bidding game. So we have, okay, I won't describe it in detail. We have some partial characterization of what are the best strategies that you can have when you bid against an adversary. So for every budget that you have, given your evaluation function, you can ask, what's the best bundle that you can get? I have this, that you can guarantee to get no matter how the adversary bids. So this causes an ordering of the bundles from the worst possible bundle to the best possible bundle. Let's say here there are 3 items. So that's the best possible bundle, worst bundle, and let's say here item 3 is worth less than 2 and item 2 is worth less than 1 and so on. And there's these breakpoints that once your budget exceeds, let's say this value, you can start guaranteeing getting this item or a better bundle, and below that you cannot guarantee it. And we have this picture, and this picture happens to be symmetric. So in one sense it's symmetric. So if you look what you can get, let's say with a bundle or I don't know 1/3, and with its complement, a budget of 2/3, you sum up their values like that. They're in a sense the complements of each other. So together they're exactly the grand bundle. So that we have this symmetry property, which says that half is a very special place. So it really means that if your entitlement is more than half, you can get a bundle. So you can get, let's say, either this bundle or its complement. You can get either this or that. You can get at least the better of these two. So it means you can get at least half the value when valuations are additive. So you can get at least half of the total value. So why is it important? Because if your entitlement was at least half, if you round it up to your entitlement hat, as we do in MMS hat, your entitlement is to all the items. So if you want to get half of MMS hat, you have to get at least half of the total value, and it really shows that in the bidding game you can get at least half of your total value. So that's why this is important for us. It also shows that if your entitlement is exactly half, you should be able to get exactly at least your MMS. And since both agents can have entitlement half, this means that each one of them gets at least their MMS. So if they have the same valuation function, it means that you got the MMS partition for two agents, which is NP hard to find, which means that the optimal strategy in the bidding game is in fact NP hard. There's no polynomial time strategy which is optimal for the bidding game. So we have this like understanding of the bidding game, and so using this we have a safe strategy that achieves this half of MMS hat. Like our strategy has two parts. So one is an explicit polynomial time strategy that we employ as long as your budget is less than half of the total budget. It's a complicated strategy, but it's polynomial time computable, and I will not even try to describe it. If at some point your budget is more than half of the remaining budget, you switch to the existential result that says that you can get at least half of the remaining value. And for this, we don't have an explicit strategy. But we know that the strategy exists. So for this reason, our strategy is not known to be implemented in polynomial time, but we have an approximate version of our strategy which just does achieve almost half the
Could you explain that point again? If at any point
So-
an agent has more than half of the remaining budget,
then it doesn't continue with our polynomial time strategy. But as I said, when you have more than half the budget, we have an existential proof showing that there is some strategy, we don't know what it is, that guarantees to you at least half of the value.
half of the value of the remaining item.
Yes, of the remaining assets. Okay, some additional notes on the bidding game. First, there are various variations on it, like was mentioned here. You can do a second price version of it. The winner of a round pays the second highest bid. You can choose maybe multiple items in any single round as long as you are willing to pay for each one of them. And the strongest currently known approximations for the APS, in fact, for any class of valuation functions that we know, the way to achieve it is through the bidding game. We don't know other ways. So we can show that for the APS, you can get 3/5 of the APS. For submodular, this is for additive valuations, and for submodular valuations, you can get 1/3 of the APS. And I should mention that if you go beyond that, let's say to sub-additive valuations, there's no strategy in the bidding game that ensures that you get a constant fraction of your APS, for example. So the bidding game stops being useful. Why is it not useful for general classes of valuation? For additive valuations, if you win a bid, you know what to do. You select the item of highest value. For sub-modular valuation, there is also something natural to do. Select the item of highest marginal value, and it works out compared to what you already hold. So items don't have intrinsic value. Their value depends on what you hold if your valuation is not additive. So this works for submodular, but beyond submodular, this rule does not work anymore, and there's no natural choice of what to do, and there's probably no good choice of what to do, you can prove that there's no strategy in the bidding game that offers a constant approximation of the APS or of the MMS in the equal entitlement case, even for valuation functions, classes of valuation functions, in which you know that there are allocations that do give you a constant fraction of the APS.
Yeah, well, all we've seen so far, though, it's all in the adversarial model.
Yes.
So you're assuming that the entire budget that you don't have is
Yeah.
all in one person
Yeah.
who,
Yes.
but when the budget is split among a lot of people, maybe you assume every person has at least some minimum budget or something.
Yeah, when it's split, in general, you should be able to do better because, for example, the adversary can like combine budgets of several people to give a high bid, whereas the individual people cannot do that. So maybe you'd be able to win items cheaply because nobody bids highly, has enough budget to bid. So this is just in the worst case what you can ensure. In general, you can probably ensure things which are better. So it really says, even in the worst case, worst possible situation for you where all the budget is just with one other person, all the remaining budget, and this other person has the same valuation as you can guarantee this much, and in better situations, you get better things. So we can ask what happens regarding best of both worlds. We said that ex ante we can get a constant fraction of the MES head, and we can get ex post a constant fraction of the MMS head. Can we get both together? The answer is no. So suppose there are only two identical items and three agents, and these are the entitlements. Two of them are just above 1/3, and one of them is just below 1/3. So each of the first two agents, when you round up their entitlements become half. So each one of them thinks that he is entitled to one item ex post. And if he doesn't get an item, gets 0 items, there's no approximation of the MMS head. So he has to get ex post an item. So it leaves no item for the third agent, but the third item thinks that ex ante, since he has positive entitlement, and ex ante is entitled to some positive value, non-zero, so sometimes you should get something, but you're not allowed to give him something. If you give him something, some other agent gets nothing, who's entitled to something ex post. So either agent 3 gets nothing ex ante, or some other agent at some ex post allocation gets nothing. So the requirements are incompatible. You cannot have the best of both worlds result here. So what's the summary for additive valuations? So ex post, you can ensure every agent at least half their MMS head, and hence at least half of every feasible share, no matter what share an agent wants to think of. If it's feasible, you get at least half of it. And this is best possible, this ratio of half. Ex ante, you get 0.591 of the MES head, and again, this is best possible, and there are no best of both results. In every randomized allocation, regardless if you try to use the bidding game or whatever, doesn't matter. Just if you give every agent positive value ex ante, then in the support of this distribution of allocation, there is an allocation in which some agents get 0 value ex post, even though you should get positive value ex post. So we'll end by considering chores. So we saw them before. These are items of negative cost. So in this case, agents said, instead of entitlements, we can think of it as responsibilities, so that they need to contribute towards taking upon themselves some items. And so they aim to minimize the cost, not maximize. And the share bounds the maximal cost that the agent might suffer. So we can adapt the definitions to chores. So maximum changes to minimax. Ex post dominating share, you need to round entitlements each time down instead of up. Responsibilities are rounded down instead of entitlements which are rounded up. So we'll not go into this much. So for chores, we do have, with additive costs, we do have a best of both worlds result, unlike for goods. So there is a polynomial time randomized assignment algorithm that for every input instance with additive cost functions and arbitrary responsibilities, output is distribution over assignments for which for every agent we have the following thing. Ex ante, the agent gets a cost of at most her proportional share. So if you compare the proportional share to this upper bound, to this MES rounded down, it's at most twice of this, because if your entitlement was almost, responsibility was almost 1, your responsibility was rounded down to half. So it's a factor of 2. And ex post, you get at most twice of your minimax share in this case. And in both cases, the approximation ratio of 2 is the best possible, even if you just don't want the best of both worlds result. You just want just the ex post result alone, or just the ex ante result alone. So this is really a best kind of best of both worlds result that we can hope for. So I'll say something about the proof. Okay. So there's it's based on a general technique that is helpful also in other situations. This is a faithful implementation of fractional allocations. So let me explain what they mean. So we design a fractional allocation with good fairness properties. So what is a fractional allocation? So agents can get fractions of items. So let's say item number 1, you can give half of it to one agent and half of it to another item. So how do agents value this fractional allocation? We look at additive valuation. So if you get, let's say, 1/3 of an item, it's worth for you 1/3 of the value of the item. Okay, so just in a natural way, we extend the valuation also to fractional values. So given a fractional allocation, what is the allocation that is faithful with respect to this fractional allocation? It is an integral allocation in which every agent gets the same value as in the fractional allocation up to one item. Okay, so it's up to some rounding effect, and the rounding effect is you can differ by the value of one item from what you get in the fractional allocation. And what is the faithful implementation? It's a distribution over faithful allocations, where the expectation of the distribution is exactly the fractional allocation. So this is a distribution over allocation, such that if you pick at random an allocation from this distribution, and I look at a particular item, the probability that I get it is exactly equal to the fraction of that item that I got in the fractional allocation. So why do we want fractional implementations, these faithful implementations? Because it gives best of both worlds type guarantees. Ex ante, you get exactly what you get in your fractional allocation, exactly the same value. And ex post, you get exactly the fractional, what you get in the fractional allocation up to one item. So this is the type of guarantees that you get in both of them. So there's some work on it, let me skip it. And here's a lemma that is worth knowing, that every fractional allocation can be implemented in polynomial time as a distribution over polynomially many integral faithful allocations, as I said before. So what does it mean? Again, let me say, so you have this fractional allocation. I can write it as, I can have integral allocations. So this is one allocation, so it says which item goes to which agent. This says, again, a fresh allocation and so on. Each one of them gets a probability. The sum of probabilities is 1. And if you sum up this weighted sum, you got exactly this fractional allocation. And each one of these allocations is faithful. As we said before, every agent receives the same value as in A star up to one item. Okay? The proof is not so difficult and very instructive of this lemma, but for lack of time, let me skip it. It's based on the Birkhoff-von-Neumann theorem that says that you can decompose any doubly stochastic matrix into a weighted sum of permutation matrices. And once you have it, it's like a black box reduction to this theorem, which is pretty easy and straightforward. But let's say for lack of time, I will not describe it. I mean, each one of these slides is pretty simple, but let me skip it. And this algorithm produces an implementation, and this implementation is faithful. So everything is very easy. It's really not a difficult proof. It can be shown, but I don't want to take too much of your time. So the slides would be available. I recommend that you look at it if you don't, because it's a nice proof, and this lemma is very useful in many situations. So again, this was the lemma, that every fractional allocation has this faithful implementation. How do we use it? So recall that we said that we had a best of both worlds result for allocation of chores when we have additive valuation. So how is this proof? It's just a one-line proof. So you start from the proportional fractional allocation in which each agent I gets a PI fraction of each item. So in this fractional allocation, each agent gets exactly her proportional share. And now you take a faithful implementation of the proportional fractional allocation. So it's a distribution over integral allocation that on average gives this proportional fractional allocation. So ex ante you get exactly your proportional share, and it's okay, so this is exactly what we wanted to give ex ante. And ex post, because we are dealing with chores, and up to one good approximation, ex post is a good approximation for chores. It's a horrible approximation for goods, because if you get, okay, if you got what you need to get up to one good, when it's goods up to one item, so let's say your MMS said that you had to get one item, so instead of that you get 0 item, you get nothing. But for chores, if it said you had to do just one chore, and instead you do 2 chores, it's just a factor of 2. So for this reason, and with some algebra, you get a factor of 2 approximation. It's pretty easy to show that you have a factor of 2 approximation if I did not round down my responsibility. Because of the rounding down, the proof is slightly more complicated, but not much more complicated. Okay. So as a summary, here's a question that we can ask ourselves. So when agents have arbitrary entitlements and assume to have additive valuations, which allocation mechanisms can we recommend? So part of the reason to study the questions about fairness and deep definition is that at the end we want to recommend some allocation mechanisms. So what I'm saying is that the mechanisms that I showed here are, you can plausibly use them. So the bidding game is something that does make sense, and it seems like a fair way to try to allocate items, like initially each agent gets a budget equal to their entitlement. Seems like some fair procedure. And also we showed that the agents have safe strategies, that the guarantees that they give in some sense are best possible, like in some worst case sense. So nothing can go too wrong with this allocation. Agents have strategies that protect them from things going awfully wrong for them in this allocation setting. So this maybe justifies using something like the bidding game, really using it as an allocation algorithm. And if you have chores, then starting from the proportional allocation and doing a faithful implementation, you can also say it's something that maybe reasonably you'd like to do. And again, nothing can go too wrong with this, because we have both the ex post and the ex ante guarantee. So, okay, so here there's no theorem behind this, it's just some speculation that the kind of ways in which we prove that you can give some approximations to shares are not through convoluted allocation algorithms, but through mechanisms that actually make some sense. So let me end with some open problems. So first, I did not discuss this here, but I don't know of any version of NV-freeness that applies to arbitrary entitlements beyond the additive case. For additive valuations, there are maybe reasonably good suggestions, but for general classes of valuations, and what do I mean by a useful version of NV-freeness? So first, we want to capture envy in the sense that people really envy. So of course you can define some property and say, I call this envy-free, but if this does not capture what people would really think, I envy this other agent because he got that, then it's not a useful definition. So in this respect, I want this definition to be useful, and also useful so that you can prove something about it. So this is one type of conceptual questions. And here are more concrete questions for additive valuations. So we showed in the first lecture in the morning that the best approximation ratios that we can hope for the MMS are between something like 3/4 and 0.98 or something like this. But the negative examples hold only when n is small, the number of agents is small. There is the possibility that as the number of agents grows, the approximation ratio improves. That it's easier to find allocations that give better and better approximation of the MMS as the number of agents grow. So it's an open question whether this is true or not, and this is a question I like about approximation of the MMS in the sense that it's a qualitative kind of question, not quantitative. So what's the best approximation ratio for the MMS? It's a quantitative question. It's an interesting question. My conjecture is that it will never be solved, but this would possibly be solved. Another thing, I mentioned that MES is not a feasible share, not even if MES, like the down MES, like the case where agents have entitlement 1/2, 1/3, and 1/6, and they all have the same additive valuation function, still you cannot give each agent per MES. But what happens if at least one of the agents did not have an entitlement of the same, that looked like 1/k, so you had to round it down. So now the total entitlement after the rounding of the agents is smaller than 1 after the rounding. Would this make the share feasible? This I don't know, and again, it's a qualitative question, not a quantitative one, and I think it's an interesting question. And another question that I find very interesting, that I did not get to discuss it, is when we go beyond additive valuations. So if we look at sub-additive valuations, there are easy examples showing that you cannot give agents more than half their MMS. It's not known if there are allocations that are guaranteed to give every agent a constant fraction of their MMS. It could be that half MMS is the right answer. And if it is, I think it would be very interesting to say that even for the general class of sub-additive valuations, you have a reasonably good approximation of the MMS. Once you put in complements, then there's no approximation of the MMS at all. But for sub-additive valuations, there might be quite good approximations, and like there's a big gap in what we know there, here. So I think that's also a very good open question.